So let's look at this problem from our discussion. Two astronauts, each having a mass of 75 kilograms, are connected by a light rope 10 meters long. They are isolated in space and are initially revolving around their common center of mass once every 6 seconds. So let's kind of draw a picture. So here's, so I'll try to draw some astronauts. So here's astronaut 1, here's astronaut 2. They're connected by a rope and they're revolving in a circle. So we'll say that they're kind of going around this way, so maybe in like the plane of the picture here. And so what's happening is these astronauts are pulling on this rope, and they're going to sometime later they're going to pull on the rope, so they're closer to each other. So they'll still be spinning, but they're going to be spinning faster. And the whole time they're sort of spinning around an axis. I'll draw the axis kind of like this here. And again, the idea here is that they're sort of rotating into the plane of the picture. Now, the key here is that these astronauts are isolated in space. So that means there's nothing that's applying a force on them. So if we think about them as a system, there can be no external forces, and at the same time, because of that, no external torques. And so we're going to say that the angular momentum is going to be conserved for these astronauts. And so we'll see them revolving around. And so let's go ahead and look here. So what I'd like you to do is maybe stop for a second and sit down and try to calculate the angular momentum of the astronauts initially. And so here's our equation for angular momentum. So it's the moment of inertia initial times the omega initial. So go ahead and give this a go, and we'll talk about it in a second. Okay, so let's think about this. So what's happening is we're rotating about this point here, and so this is going to be the case where we can treat the astronauts as a point mass object. And what I'm going to do is say, okay, so then this is the r, the distance out to the astronauts. And so for the moment of inertia, what I'm going to say is there's going to be the mass for the first astronaut. They both have the same mass of 75 kilograms times r, we'll call it r initial squared, plus m r initial squared. So I'll call this the r initial. And so we're doing the point mass. Remember, moments of inertia for objects that are point mass is just the sum of the masses times r squared. And so here we're going to call this ri. And then that equals omega I. So that would be our initial angular momentum. So if I clean this up a little bit, I'd get 2m ri squared omega I. And so let's think about this real quick, just kind of put some numbers here. So we're told that the separation between the astronauts is what? Is 10 meters. So this r is actually going to be 5, but we'll kind of think about that later. And so it's sort of giving us here the total length between them. And then what we're told is that they pull in the rope having the distance. And so over here, this may not be to scale, but the idea is that the distance between them is now 5 meters in the end. And so the question we're asked is how much work is done by the astronauts. But let's just kind of start by thinking, okay, so we're going to use angular momentum to figure out how fast they're rotating after they do this. And again, it's like problems we talked about in class. As the astronauts kind of get in, it's sort of like the ice skater. So as they come in, they're lowering their moment of inertia. We'll find that the moment of inertia will get lowered, and the omega, how fast they're spinning, should be increasing. So we know what our initial Ri is. Now, the one thing we don't know right away is the omega. And they give us some information here. So they tell us that the astronauts are initially revolving about their common center of mass once every 6 seconds. So let's think about that. You guys maybe go ahead and pause this and take time out for a second to try to figure out what that omega would come out to be. Okay, so we want our omega to be radians per second. And so if I revolve once every 6 seconds, then what that means is I go through a total angle of 2 pi once every 6 seconds. So it should be 2 pi divided by 6. And when I plugged this in, I got something like 1.047 radians per second. So that's our initial omega I. And so then to set this up, we'll say our angular momentum final, which would be m r final squared plus mr final. So again, it's the same type of moment of inertia. We're doing the point mass equation, and then this would be omega final. And so when I'm all done, I get 2m r final squared times omega final. And so what do we want to do? Well, we want to set these two equal to each other. So I want to say Li equals Lf. So I want to take these two expressions and set them equal. So my initial is 2m r initial squared omega initial, and my final is real similar looking, just that we sort of just changed those distances. And hopefully this, what's going on here, makes sense. It's like in this final case, the r goes down, so the omega should go up. That's the idea. We're going to expect that this increases. So what's nice about this is I can just cancel out the 2m, since that doesn't change in the problem, so that just cancels right out. And so I can get an equation for omega final is going to equal ri squared divided by rf squared times the omega initial. And so again, we can put numbers in here. The r initial, that radius, remember, was 5 meters, right? Because it was a total of 10, so the ri would have been 5. And so it would be 5 meters squared divided by 2.5 meters squared. And then our omega initial was that number, the 1.047 radians per second. And when I calculated this, I came out with a number 4.188 radians per second. So it did exactly what we thought. It's going to increase its angular velocity. And again, just to reiterate, what's going on here is because the astronauts are isolated, we're going to conserve their angular momentum of their system. And that's what we did here. We calculated the initial and the final. So we're very similar to stuff that we used to do with linear momentum, just now we're doing this with angular momentum. And so finally, how much work is done by the astronauts? So different ways to do this, but I want to say that the total work, right, our sort of one of our fundamental equations, is equal to the change in kinetic energy. And so what is that kinetic energy now? Well, it's a little bit more complicated. And so I've got my moment of inertia initial times, or I'm sorry, that would be the final case. So moment of inertia final, omega final squared minus 1/2 I initial omega initial squared. So again, we have all of this information. And so let's go through and write this out. So we have the 1/2. Our final moment of inertia was 2m, the radius final squared, where again, let's just remember that that radius final for us was 2.5 meters. Also, the mass given in this problem is 75 kilograms. And then all of that times our omega final. Remember that for omega final, we got this number of 4.188 radians per second. And this will be minus 1/2 2m our initial squared omega I squared. So we're subtracting out these two pieces where the tricky part, at least one of the tricky parts, is figuring out this moment of inertia. And again, this Ri, if you remember, was 5 meters, and then our omega initial was something like 1.047 radians per second. And so now I just plug all of this in. So one thing that's nice is the 1/2 and the 2, those two guys just sort of cancel. So we can clean up that just a little bit. And so we have a mass of 75 times R final. It's just from right over here. Is again this 2.5 meters. And then our omega final squared is the 4.188 radians per second. So all that squared, and then minus from the other side, 75 kilograms. Again, the initial distance, the initial radius was 5 meters, is Ri, and then we have the 1.047 radians per second squared. And when I did this, the number I got was something like 6.16 times 10 to the 3rd joules. So in doing this, the astronauts did positive work on their system. They added kinetic energy, added mechanical energy to the system here of an amount 6.16 times 10 to the 3 joules. So they added that much kinetic energy, and again, that's the work that they did. Okay, so hope this helps.